Okay, in this video, it's kind of a continuation of the first video for section 13.4, but we're going to focus on the acceleration vector here. And we're going to show that the acceleration vector can be written in terms of the unit tangent vector and the unit normal vector. Here we go. So let's start off with this. So we're going to look at the components of the acceleration vector and try to write them in terms of t and n. Okay, here we go. So first of all, the definition of unit tangent vector is r prime over the magnitude of r prime, which is just the velocity vector over the speed, right? So if you solve it for the velocity vector, you get the velocity vector is the speed times the unit tangent vector. Differentiating with the product rule, right? This is the product of two functions. One's a real valued function, the other one's a vector valued function, so you got to use the product rule, right? Anyway, so we get to this. Now remember, the curvature is defined in terms of the magnitude of the t prime over r prime. So if that's the magnitude of t prime over v, if you solve this for the magnitude of t prime, you get that magnitude of t prime is the curvature times v. So hold on to that for a minute. We'll come back to that in just a second. The unit normal vector is defined to be t prime over the magnitude of t prime. So if you solve for t prime, you get that it's the magnitude of t prime times n, and we just showed that the magnitude of t prime is the curvature times the speed. So you could replace magnitude of t prime with curvature times speed times n. So then when you go back to the acceleration vector, we're going to replace. Go back to here. We're going to replace t with t prime with k times v back in here. So the acceleration vector becomes the v prime, the magnitude of the speed times t, plus k v squared times n. That's what we wanted to show. The acceleration vector is the change in the speed times the unit tangent vector times the curvature times v squared times the unit normal vector. That's what we wanted to show. Now, interesting question here is, if a particle moves along a straight line, what can you say about the acceleration? Well, if the curvature moves along a straight line, isn't the curvature zero? So that means that the acceleration vector is tangent to the curve, right? And if the particle is moving with constant speed, if the speed doesn't change, what can you say? Well, if the speed doesn't change, then the derivative of the speed is zero. So that would mean that the acceleration would be pointed inward, right? Would be pointed inward along the unit normal vector. That's what I wanted to show. The other thing I wanted to look at here, this is more of a computational thing. So this is where we're at. The tangential component is v prime. This is the derivative of the speed. And the normal component is the curvature times v squared. So this is what we wanted to show. Now, from a computational point of view, these are kind of hard to compute, so there's an easier way to write these. That's what we're going to do now. We're going to express these in terms of cross products. Here we go. So let's start off with this. V dot A, using properties of dot products. This is V. Remember, V is V times the unit tangent vector. And we just got through showing A is this. So properties of dot products, you dot this with this, and you dot this with this, and you add them together. T dot T is 1. It's actually the magnitude of T squared, right? So the magnitude of T squared is 1 squared. So that's why this is equals 1. And T dot N is 0. Now that's because they're orthogonal, right? So anyway, so it just reduces down to this. So therefore, the tangential component of the acceleration is the speed. It's v prime. If you solve this for v prime, you get v dot a over v. The speed. So the speed is by definition the magnitude of r prime of t. So to find the tangential component, just dot r prime with r double prime and divide by the magnitude of r prime. That's much easier to do it that way. For the normal component, it's k, it's a curvature times v squared. So we actually derive this from 13.3. This is the curvature, and this is the v squared. So all you do is cancel some of the powers of r prime, magnitude of r prime. So this is how you could. This is a much easier way to compute the normal component of the acceleration. So for example, here's a present problem. If you're given a vector valued function, find the tangential and normal components. The tangential one is easier to compute. It's just the dot product r prime with r double prime over the magnitude of r prime. R prime is this, r double prime is this. The magnitude of r prime is 4t squared plus 10. So you get this. Now for a normal component, you have to cross r prime with r double prime and take the magnitude. I get that over here. And then you divide by the magnitude of r prime. That's it. Talk to you later. Bye-bye.